Uh, Hello, good morning, everyone. I want to welcome you to another statistical class. Of course, today we're starting a new chapter, and this is Introduction to Normal Distribution. I think the class is getting more complicated. We are actually um, you know, we are reaching an advanced stage in the work. And of course, if you really want to understand, of course, you need to be able to pay attention to notations and, the reason why we do what we do with that. I want to believe we understand. Okay, so um, in the outline, today we're going to achieve univariate normal. On Wednesday, it's going to be bivariate. And of course, on Friday, multivariate and sampling distributions. I want us to go into univariate normal. Now, but before going into univariate normal, why do we find ourselves, studying univariate normal distribution? I'm actually going to say this in a stochastic environment, in a world that we find ourselves. Of course, we know things are changing. There's variations in the world. If you want to talk about whether in stock returns, or you want to talk about oil price, or you want to talk about in politics, or you want to talk about in economic cycle, is things are changing. And of course, the only way to understand the movement of random variable is to have a way to understand the way they are distributed. I'm going to say that again. Events in the world, whether in economic world, whether in sociological world, or whether in political world, okay, events are actually defined as random variable. Okay, they are random variable because they varies, randomly. And of course, in a situation where we really want to understand, the variable, we need to first understand the way the variable is distributed, the way the data set in the variable is distributed. So because of that, we need the idea of probability distribution. So probability distribution will give us an opportunity to be able to know the possible values, a random variable can take with corresponding frequency, a corresponding probability. So when I say frequency, I mean probability. So frequency means the number of time a particular the value of a random variable will occur. Of course, we all know, a particular value of a random variable will occur more frequently than other. We do not expect them to have the same rate of occurrence. So if we want to understand, uh, you know, a random variable in a stochastic world, okay, whether blood pressure or height or weight, all of that, they are random variable. And of course, we need to be able to understand the probability distribution if we really want to understand something that has to do with them. Now, we have different kind of probability distributions. We have normal, we have binomial, we have Poisson distribution, we have hypergeometric, gamma, Weibull, Nakagami, Maxwell. There are so many of these distribution that is more or less synonymous with having countries. Every country has a map. If I really want to have a sense of somebody, if I understand where the person come from, there's possibility I should be able to say something about that person. If I have a random variable, which could be a blood pressure, it could be a price, the stock price, GDP, and so on like that. If I really want to understand, the random variable, then I need to know the probability distribution it come from. Now, there are different kind of probability distributions, but let me tell you this. There is a particular distribution that is an household name in statistics world and in machine learning world in general that we call normal distribution. Now, I'm going to first give you the history of normal distribution before we go into the mathematical properties of normality. Okay, so the normal distribution was actually um, you know, if we want to trace the history of normal distribution, it can be traced to three scientists. The first one was actually Abraham de Moivre in 1733. Okay, now let me tell you this. Abraham de Moivre was trying to solve a problem in 1733. He was actually studying, uh, gaming probability. And of course, he was trying to look for a way to approximate large numbers, okay? Large trials, okay? Large trials. Of course, uh, in a game of gambling, where it's either somebody wins or loses, of course, if we want to model occurrence in that situation, we're actually going to go binomial. Okay, we're actually going to go binomial. We're actually going to go binomial. Binomial distribution is actually a probability distribution for modeling events with two possible outcomes. So two possible outcomes because say that you win or you lose, just like maybe going for election, somebody lose or somebody win in investment or somebody gain or loses. Now we're actually going to use binomial distribution in that regard. But in a situation where the sample size in binomial distribution is very large, okay, using binomial distribution will be cumbersome, will be complicated. And as at 17, 30 something, of course, you know, uh, I don't believe they have a computer that can, maybe they have computer at that time that can handle that kind of situation. So, situation where the sample size is very, very large, of course, using using binomial will be cumbersome. And let me also tell you this. De Moivre was trying to solve, there was a problem that was put forward by a Dutch scientist called, I'm going to write the name for, wanted to have that on record. We call the scientist Grace Sandel. Grace Sandel was actually a Dutch. Okay, he was a Dutch mathematician, and the Grace Sandel wanted to solve this particular problem. They want to figure out what is the probability of this. 5, 7, 4, 5. Okay, and X, X lie between that and this, or 6, 1, 2, 8. I think this question has to do with death rate in the United Kingdom. It was trying to model the probability of having the number of deaths, or probably to be between that And of course, give me 1 second. I think I'm gonna clean. And of course, the probability is going to be half. Okay, P, given that P equal 1 over 2. Okay, given that P equal to 1 over 2. Now, if you want to solve this problem, because S, okay, is dichotomous, okay, it's either death or not. That's all we mean. You want to figure out the probability that the number of deaths, okay, Abraham Dimova was trying to figure it out because it was a graveside problem. Okay, Graveside, a Dutch mathematician, was not able to figure this out because to figure this out, you're actually going to use this. You're actually going to use this binomial density where you're actually going to start your summing. You're going to sum, okay? You're going to sum, okay? Without wasting my time, maybe I'm going to call this A, this B. A is 5,745. B is 6,128. So S start from A to B, okay? And of course, in solving that, okay, it means the totality of number is 11,029, okay? So combination S, right? Combination S, and of course, half raised to power 11,000, 11,429. Please pay attention. This was a graphicide problem. Okay, Graf Sandy, a Dutch mathematician, wanted to figure out this problem. And to figure this problem out, okay, he's going to use binomial. But binomial distribution, because the sample size is large, the sample size is 11,429. Okay, using binomial distribution is going to be complicated. But do you know what Abraham Dimova did in 1733? Abraham Dimova was able to approximate binomial with a normal distribution. Abandimova proved that when sample size is large, binomial distribution becomes normal distribution. So he used the idea of a normal, we call that normal approximation to binomial. Normal approximation to binomial. Okay, now he was able to solve this problem using normal approximation to binomial. I think I'm actually going to quote his approximation here so that you'll be able to see. Okay, it was able to having this x minus n over 2, okay, less or equal to d. Okay, so n combination s, which is binomial, n combination s. N is the numbers of trial, s is the characteristics of interest, half raised to power n. Okay, raised to power n, he was able to approximate that, okay, to be 4 divided by square root of pi. Okay, 4 divided by square root of pi. Okay, 4 divided by square root of pi integral 0. Okay, all the way to d divided by root n. D divided by root n. Okay, exponential raised to power minus 2y squared. 2y squared the y. So which means he was able to approximate a large sample size problem. Okay, was able to use normal approximation. He was able to use normal to approximate binomial, and at the end of the day, he got a result. So he was the first person to actually use the idea of a normal distribution to approximate a scenario when sample size is large, and he called this our paper article normal approximation to binomial. Okay, now, like I said the other time, you know, if we can trace the development of normal distribution to three fronts. The first front was by Abraham de Moivre in 1733. Okay, so Abraham de Moivre in 1733 actually, uh, you know, used what I call normal approximation to binomial. That was the first time we heard about binomial. But let me tell you this, 50 years after, okay, the story continue. Okay, 50 years after, has anybody heard about Laplace? Okay, Laplace, maybe in 1783, use this distribution, to as a measurement of errors. That's why today in statistics, whenever you hear about the probability distribution of errors, of course, normal distribution is being assumed. Okay, use that to solve, use that on astronomical data. But let me tell you something. There was one person that popularized normal distribution, and that person was Carl Gauss in 1809. Gauss. And today, that is the reason why normal distribution can also be called Gaussian distribution. You know what Gauss did? Gauss provided statistical properties of normal distribution. He derived the mean, he derived the variance, he showed us this. He was able to show us what you are seeing right now. This can be attributed to Gauss. Okay, Gauss actually popularized, okay, this distribution. Now, I want to define this distribution now, okay, with regard to X. Here, I'm only talking, when I say univariate X, I'm only focusing on one measurement at a time. Maybe I'm focusing on blood pressure, or I'm focusing on stock price, or I'm focusing on certain characteristics of interest. Now, because blood pressure is a random variable, weight is a random variable, stock price is a random variable, and I want to understand a random variable, the best way to understand a random variable is actually to understand the probability distribution. And let me tell you this, some of natural and social phenomena exhibit this distribution, normal distribution. Okay, now this is a formula, this is a density function of a normal distribution. It has two parameters, the mean and the standard deviation. The mean is the mean, okay, we shall, or it could be positive or negative or zero, mean slice in real number, and of course the standard deviation and the variance, the sigma, which has to be greater than zero. Okay, now symbolically, if I want to write that a random variable x follow a normal distribution, this is the way I'm going to put it. Okay, that means x follow normal distribution with the mean of that, the variance of that. The two parameters of a normal distribution are mean and variance. Okay, now I need you to pay attention. If you take a look at this density, this equation one, okay, if I want to, let me tell you this, what is the significance of a normal distribution? Like, why is it that in statistical framework, we normally celebrate if data set follow normal distribution? And I'm going to tell you now. Number one, okay, before going into that, I think I remember what Laplace also did, because I told you initially Abraham de Moivre was trying to solve a graphicide, Graves-Sander problem of that required the use of binomial distribution, but because of this the fact that the sample size is large, that using binomial became complicated, and of course Abraham de Moivre came in and he used a normal approximation to solve the problem. But let me also tell you this: Laplace also did a wonderful job. Laplace was able to prove that even though we got some, maybe data set come from a distribution that is not normal, okay? And he said, if we compute average repeatedly from from the distribution that is not normal, provided the sample size is large, okay, the distribution of the mean will follow normal. I'm going to say that again because that is the basic rock of statistical inference. Without that assumption, it will be very difficult for us to test hypotheses and for us to construct a confidence interval in statistics. Now, I'm going to say that again. Laplace actually said if we are sampling from a probability distribution that is not normal, but if we choose a sufficiently large sample, the distribution of the statistic, okay, when I say statistic now, I mean the means, several means, repeated means that you compute from such population, provided if the sample size is large, the distribution will be normal. And that's what we call central limit theorem. That can be attributed to Laplace in 1783. Now, I was talking about what is the significance of a normal distribution. Why do we need to celebrate? The significance of a normal distribution is because it provides, a technique. Okay, it's a foundation of statistical inference. And why does it provide a foundation for statistical inference? Because even though we are sampling from a distribution that is non-normal, provided a central limit theorem applies, of course, the distribution of the statistic will be normal. Okay, that is one of the benefits. Another, and why is it that becomes, why is it that is possible? That is possible because when data sets follow normal distribution, okay, normality, okay, translate into standardization. I'm going to say that again. Normality translate into standardization. Now, if you take a look at equation 2, okay, that is a standard normal distribution. Okay, you're actually going to see here what is the difference between equation 1 and equation 2. Okay, when you take a look at equation 1, okay, the mean is mu and the variance is sigma squared, but in equation 2, okay, I can get equation 2 from equation 1 when I plug in me to be 0 and the variance to be 1. Why am I doing that? I'm doing that for standardization, because if I don't do that, if I want to use this particular density to figure out a probability associated with a random variable, I'm actually going to run into calculus complexity. Imagine I want to find if X is my blood pressure and I want to find, okay, let me pretend I want to find what is the probability of my patient having a blood pressure maybe greater than A. Okay, if I want to do that, because this guy is a probability density function, I will need to integrate, okay, I will need to integrate from A to infinity, then ds. Doing that will require, we're actually it's gonna land us into calculus complexity, rigorous calculus. But with standardization, okay, you having this, it will be easy for us to compute probability associated with a random variable. Simplicity of or probabilistic computation. That is one of the benefits of a normal distribution. Does that make sense? Because with this, with the standard, with standardization, we can make use of a z-score. Has anybody heard about z-score? We can make use of a statistical table. Does that make sense? Okay, that is the essence of standardization. And let me tell you this. Do you know that if I have different kind of data set, maybe I have data set on blood pressure, I have data set on weight, I have data set on maybe on another variable, or let me say this, and I want to compare across data set. Don't forget, each variable we have their means, we have their variances. Imagine I have 1,000 different data set. Is a set of data, number one, another set of data, another set of data, another set of data. Even if each of them follow normal distribution, that we have different means, that we have different variances. But what is going to make comparison to be effective is to standardize them. When I standardize, then, okay, all of them, they will have the same mean is zero, and they will have the same variance. Does that make sense? So standardization, okay, will make us to have effective comparison among data set. Okay, now there's so many benefits of normal distribution. Let me also tell you this. Most of the hypothesis testing in statistics rely on the assumptions of normality. I'm going to say that again. Most of the hypothesis testing in statistics rely on the assumptions of normality. So you can see significance of normal distribution. Okay? Now, that's been said. Now, if I have, just like what I said the other time, if I have a normal distribution, and of course a normal distribution because the f of s is a PDF, probability density function. Okay, the random variable s is continuous. Okay, if I want to find what is the probability of x lying between a and b, I should be ready for calculus. Okay, I should be ready for calculus without standardization. Okay, so what this guy is trying to say, what is if X is blood pressure, what is the probability that my patient will have a blood pressure between A and B, maybe between 16 and maybe between 100 and 120 or something, then I should be ready to perform an antiderivative on the density of a normal distribution, but that would be complicated. But with standardization, okay, standardization will facilitate easy probabilistic computation. Now equation 4 is getting a CDF that we call a cumulative density function. Okay, and of course we believe the CDF will lie between 0 and 1. Now let me tell you this. The breakthrough in parametric testing, the breakthrough in statistical inference. When I talk about statistical inference, I mean testing hypothesis and constructing confidence interval. All of that become possible because of the fact that we rely on assumptions of normality. Okay, now how am I going to know if my random variable follow normal distribution? Because let me tell you this, when you are working with data set, when you are working on data set, you need to be able to understand the distribution of your data before moving forward. Now, how am I going to know? I can know so many ways. I can know by, this is what we call empirical rule. By empirical rule, if data set follow normal distribution, we expect, 68% of the data set to, to be within one standard deviation. Do you know how they derive that. You can try that how. Okay, they do integral, okay, mu, okay, minus sigma, okay, mu plus sigma, okay, then f of s. F of s is going to be the density function of a normal distribution, okay? When you integrate that, when you perform an antiderivative on that, what is going to give you is going to be 0.68. That is how they come, that's how they know, okay? You know, mu minus sigma is one standard deviation below the mean. Mu plus sigma is one standard deviation above the mean. Now, when you, and that is taking place here, take a look at this, take a look at this side. The mu here is the center, okay? One standard deviation, you know, is, we are trying to talk about, this is one standard deviation below, one standard deviation above. And that's exactly what we're trying to do. We're talking about area under a curve. The total area under a curve is going to be 0.68. Now they arrive at that by performing an antiderivative on the density function of a normal distribution, which means, okay, if data follow normal distribution by empirical rule, 68% of the data set will be within one standard deviation. Now, if data set follow normal distribution, 95% will be within two standard deviation. You know, if I put 2 here and I put 2 here, okay, I'm not going to get a 0.68 anymore. It's going to be 0.95. If you try your calculus, okay, it's trying to tell you, and that is what this guy is trying to say. All the area here, that will be 95%. 95% of the data set, okay, will be within two standard deviation. Two standard deviation where you have two standard deviation below, two standard deviation above. But you know what? When I change that to 3 sigma, when I change that to mu minus 3 sigma up to mu plus 3 sigma, okay, and I perform an antiderivative on f of s. Don't forget, f of s is the density of a normal distribution. Okay, this is actually going to give me 99, maybe 0.9975, which is nearly all the data set would be within 3 standard deviation. Okay, this is what this can be called empirical rule, using empirical rule. Okay, this is using empirical rule. Okay, now that is what this picture is actually showing. This is a double bell shape. This shape actually depicts some of biological and social phenomena. Okay, now if you take a look at this now, okay, at times there's possibility I have different kind of data set. Okay, if you take a look at this, they have a center 0. If you take a look at what I have here, okay, if you take a look at that, the center is actually 0, but the way they spread out is not the same. Data set could have the same average, but they have different standard deviation and variance. This is what we're just trying to show here. And this is a cumulative density function of the, of different values of parameters, which means if I vary the parameters of a normal distribution, I'm actually going to have different shapes, even within the normal density. Okay, I needed to pay attention in a situation where X follow normal distribution. If X happens to be the price of a product, If you don't cite example, you may not understand what you're doing. I understand my math. I understand my start by relaying every notation to real life. Now I want to give you an example now. If X follow normal distribution, you know what I mean? If let's assume X is a price of a commodity and the price of a commodity that changes, okay? If it changes, a typical example could be oil price. If we assume oil price to follow normal distribution with a mean mu and sigma squared. Now, let us now define another variable that could depend on oil price. Okay, maybe let's call Y revenue. Okay, revenue. I'm just assuming if Y is a revenue, okay, if Y is a revenue, okay, and X is price, and X is price. If X is a random variable, and if Y depend on X, Y is also going to be a random variable. If price is a random variable following a normal distribution, Y depend a linear combination of Y and S is also going to be a normally distributed. That is exactly what I'm trying to point out. Take a look at this guy. Okay, I know that X follow normal distribution and Y equal to AS plus B. Okay, if I take the expectation of Y, of course, I'm actually going to have yeah, if I take, because the way to find the mean of a random variable is to take the expected value of Y is going to be expected value of AX plus B. AX, AX plus B, right? We've done this in a lower level of statistics. Now here is going to be A, expected value of X, expectation of a constant, because here A and B are constants. Okay, expectation of a constant is going to be a constant. I'm actually going to have that guy plus B. And right now, what is expected value of X? The expected value of X is actually going to be the mean. Okay, so, and that is the way, if you take a look at this, A mu, okay, so if I want to, rewrite uh, what I have here, I'm actually going to write A, expected value of S is mu, then plus B. So which means the mean of Y, which is revenue in this case, is actually this. Then the variance. What is the variance of AX plus B? Okay, the variance of AX plus B. A is a constant, B is a constant. So here, I'm actually going to have the variance into AS plus variance of a B. Variance of a B, variance of a constant is 0. A constant doesn't change. Now, if I have a variance of AS, in statistical analysis, the constant is going to come out and become a squared. I'm going to have A squared variance of X. What is the variance of X? According to this, the variance of X is sigma squared. And that was why I got A squared sigma squared. Okay? You can review your lower level statistics for that. Okay, now you can now go ahead and solve this. Take a look at that. When X follow normal distribution with the mean 1 and variance that, you can figure out the mean and variance of Y using this particular formula. Okay, I'm gonna move away from that. What is the takeaway? The takeaway here is, okay, when X follow normal distribution, if Y is a linear combination of X, then Y also going to follow normal distribution. That's exactly what we mean. Okay, you can see I've already solved the problem. You can take a look. Now, another thing I want us to talk about Please, I needed to pay attention. It's becoming complicated, and I needed to pay attention. For instance, I have data set before me, okay, and I've investigated whether graphical analysis, maybe I actually draw the histogram, or I draw the stem and leaf plot, or I draw the density plot, or I use empirical rule. Okay, whichever way that I go, okay, I discover that the distribution is normal. If the distribution is normal, then the next thing that I'm actually going to do is I want to figure out the mean and the variance from this data set. Okay, if I have if I happen to be a physician, I have patients, okay, and I measure their BP of every patient, and I plotted the that maybe on Instagram or on the density plot, or I use empirical rule, and I discover that the data set follow normal distribution. Now, if it is followed normal distribution, the next is I want to get the average. I want to get the standard deviation. Okay. Now, doing that, I want to use the method of maximum likelihood. There are different kind of method to figure out the parameters from a given distribution. Before I can use the method of maximum likelihood estimation, then I need to know the probability distribution of the data set. If you don't understand, please ask question. Now, I have my data set. Can you see that? Maybe that I said on blood pressure. And I've realized that they follow normal distribution. And right now, I want to figure out the two parameters in the normal distribution using the method of maximum likelihood. What I'm going to do, I'm actually going to start with the density function. This is the density function of a normal distribution. But you know what I'm doing here? This is actually getting a joint PDF. If I want to use method of maximum likelihood, I need to first of all get the joint PDF. The joint PDF is like multiplying this PDF in n terms. Okay, now what I'm going to do, we call that a likelihood function. Okay. Now, after that, what am I looking for? I want to maximize the joint PDF, but maximizing the joint PDF because of it's mathematical in nature. Okay. We're actually going to run into problem of mathematical complexity. What are we going to do? We can introduce a log to both sides, natural log. Introducing a natural log to both sides is going to make it additive. It will be very easy for you now to differentiate. Don't forget, we want to optimize. Okay, it's an optimization problem, and this is a maximization in optimization where I need to differentiate. Now, differentiating likelihood function will be complicated. Then that was why I introduced a log. Take a look at that. We introduce a log to both sides. Now, after introducing a log to both sides, we differentiate. With respect to mu, to one of the parameter, we set to 0, and we solve for mean. And at the end of the day, this is what we got. So what that guy mean? If I actually seeking to obtain the maximum, if I'm using the maximum value estimation procedure to obtain the mean, you know what this guy is telling me? Find the average, add the data set together, and divide by n. That is what this guy is telling me. That is how we know that we actually, if we want to find the mean, then we need to add the observation together and divide by n. Now we're going to do the same to the variance. We differentiate with respect to the sigma, and at the end of the day, this is what we got. And that's how we know the formula of the variance. Now, how do I do this in R? If I want to do this in R, this is my data set, right? This is my data set. Okay, this is the code. This is the code for maximum likelihood. And at the end of the day, when I write that, oh my God, it's just going to display the mean and the standard deviation. Look at that. Okay, so what have I done? Okay, I introduced it to univariate normal distribution. And you know what we're going to do on Wednesday? If we have two variables that are jointly normally distributed, how are we going to go about it? Okay, I want to use 3 minutes before I go. I want to give you a clue on the assignment. Now, and I need you to pay attention. This is a clue on the assignment that I posted yesterday. I mentioned total variance. Please pay attention. I mentioned total variance. I asked you to obtain total variance. Some of you may not know the difference between a total variance and a generalized variance. They are not the same. Please pay attention. Generalize, because it's in that assignment. Generalize variance. Please pay attention. Generalize variance. Now I'm going to tell you the difference between the two. For total variance, they only want you to add elements in the diagonal of the variance covariance matrix. Total variance means addition of the variances of all the random variables. It tells us the spread in the data, okay? But the issue with the total variance, it ignores relationship among variables. It does not capture covariances. Okay, but the generalized variance, if I want to find generalized variance, I need the determinant of a variance covariance matrix. Okay, if I want to find a generalized variance, I need the determinant of a variance covariance matrix. The generalized variance capture the spread in the data, and it also put into consideration relationship among the variables as well. That is the difference between a total variance and a generalized variance. If variables are highly correlated, I'm going to say that again. If variables are highly correlated, the determinant of variance covariance will be approaching zero. Approaching zero means it's approaching singularity. And you know what that means? It will create an interpretation issue. Does that make sense? Now you understand the difference between a total variance and a generalized variance. We call it generalized variance, okay, the volume of confidence, ellipsoid. Ellipsoid, in the way the data is being distributed, okay, the ellipsoid in the data. So that is the difference. So when you see total variance, if I have to compute total variance, I wanted to add element in the diagonal of the variance covariance matrix. If I ask you a generalized variance, then I'm seeking for the determinant of the variance covariance matrix. Does that make sense? Okay, sure you'll stay safe. Have a lovely day. Bye for now, everyone.